Hi, my name is Tenenbaum, and today I'll be presenting a joint work with my advisor, Professor Haim Kaplan, titled Locality-Sensitive Hashing for Efficient Similar Polygon Retrieval. Image retrieval systems are vastly used in many multimedia applications in fields such as geographical information systems, computer vision, and medical diagnosis. The databases are often huge, and querying the database for similar images to a given image efficiently is a problem of rising interest. There are two general types of metrics which define how similar two images are. Intensity-based metrics consider the color and texture at the pixel level. They are less intuitive, but easier. The geometry-based metrics, however, quantify how similar two images are based on the shapes they contain. Such metrics are more intuitive, but harder to define. In this talk, we focus on shape-based metrics. Specifically, we assume that edge detection is done and shapes are already extracted, so we consider polygons. The natural question that arises is, how do we define distance between polygons? Since we strictly consider the shape, it is clear that the distance should be invariant to rotation, scale, and translation. We use the turning function distance of Arkin et al., which is defined as follows. Given a polygon P, we represent it by its turning function, denoted Tp of x, defined to be the cumulative angle between the tangent and the x-axis as we traverse the polygon. Let's see how this polygon's turning function looks like. We start with the polygon P, then we scale it to unit perimeter. Then we define the reference point O, where we start tracking the turning function from. To the left, we'll be tracing the circumference of the polygon P, and to the right, we'll track how the turning function changes. Initially, right after we start after O, the angle that's created with the x-axis is phi 0, so the initial turning function value is phi 0. As we continue tracing the same edge, the turning function remains constant. Eventually, when we hit a vertex and turn left, we gain a cumulative angle of phi 1, so the turning function value is now phi 0 plus phi 1. Eventually, we trace the whole polygon and get the turning function to the right. Note that left turns of the polygon increase the cumulative angle, whereas right turns decrease it. Given the definition of the turning function, we can now define the turning function distance between two given polygons. To the right, we plot the turning functions, where the red one corresponds to the turning function of P, and the blue one corresponds to the turning function in parts of Q where it's different from P. Given this difference between the two turning functions, we define the turning function distance to be the LP distance between the functions. That means the integral over the whole turning function of the absolute value difference between the turning functions of P and Q raised to the power of P, all of that raised to the power of 1 over P. Note that the L1 distance between the polygons is precisely the green area. It is easy to see that this distance definition is invariant to scale and translation of the polygon. However, it's not invariant to rotation and changes of the reference point O. We therefore change the definition of the turning function distance to be invariant to these two. First, we consider two different rotations of the same polygon P, and notice that effectively rotating a polygon P and selecting the same reference point results with a direct increase of the rotation angle to the turning function. Hence, to eliminate the dependence of the turning function distance on rotations, we can simply take the minimum over all rotations of the polygon. Specifically, we define the rotation invariant distance LP up-down arrow between P and Q to be the minimum over all vertical shifts alpha of the LP distance between the turning function of P plus alpha to the turning function of Q. This gives us the argument to the right. Now, to eliminate the dependence on the reference point, we notice that selecting the reference point differently, roughly, results in a horizontal cyclic shift. It is easy to see, since when we start tracing the turning function from O counterclockwise versus from O prime, the difference is simply that O prime sees all the left and right turns before O, but the turns are the same, hence the increase and decrease in the values are the same, but happen earlier. We combine both previous methods to eliminate the dependence of the rotation of the polygon and its reference point, and we define the turning function distance between two polygons P and Q to be the minimum over all vertical shifts and horizontal shifts of the LP distance between the first turning function moved by the horizontal and vertical shifts to the second turning function. We must extend the domain of the turning function from the segment 0,1 to the segment 0,2 by defining the turning function at x plus 1 to be the turning function of x plus 2 pi, which accounts for the fact that after a complete rotation around the circumference of the polygon, we've already accumulated an angle of 2 pi. This distance is invariant under translation, scaling, rotation, and the selection of the starting point. As we can see in the slide, all the distances over polygons naturally define three distances over functions: aligned LP distances, vertical shift invariant distances, and vertical and horizontal shift invariant distances. Since our results for these distances hold for integrable functions, for ease of presentation, we plot general integrable functions rather than strictly turning functions of polygons. Now that we've defined our distance functions, both over polygons and over functions, we can give shape retrieval schemes based on those distances. An easy and efficient shape retrieval scheme based on the turning function similarity can be to simply store all of the elements of the database as is, and once we receive a query, compute the pairwise distance directly to all points of the database and return the nearest neighbor. Unfortunately, this solution is not efficient and takes time, which is linear in the database size. The question is, can we find near neighbors efficiently, specifically in strictly sublinear time of the database size? To give a positive answer for this question, we resort to an approximate near neighbors scheme. We make a small detour to present the approximate near neighbors problem and locality sensitive hashing, which is the tool we use to solve this approximate near neighbors problem. The approximate near neighbor search problem is to build a data structure given the following inputs: endpoints in some space Z, a non-negative distance function between pairs of points, a distance threshold R, and an approximation factor C, which is larger than 1. The guarantee such a data structure must satisfy is that for any query Q, if there exists a data point with distance at most R to Q, for example, this P, then we must return a point which is not necessarily P, but is within distance at most CR from Q. Again, the guarantee is that if we have a point which is very near Q, then we must return a point which is within radius at most CR to Q. We call such a data structure an RCR, approximate near neighbor, or ANN data structure. And the idea of LSH is to give such a data structure using hash functions for which near neighbors tend to collide. Here's the definition of LSH, locality sensitive hashing. Let R be the distance threshold and C the approximation ratio, and a high and low probability. A family H of hash functions from our space to a hash space gamma is an RCR P1 P2 LSH for a given distance function. If for any pair of points, if they are very close to each other, then the probability of collision over a random hash is high, namely larger than P1. And if they are not too close to each other, namely of distance at least CR, then the probability of collision is low and bounded by P2, which is smaller than P1. We demonstrate this below. We're given 3 random points from a space Z. It is likely that 2 near points collide under the same hash value 2, but 2 far points do not collide. And the following event is unlikely that 2 far points collide. Indik and Motwani, and later Harpeled, showed how to solve the approximate near neighbor problem given an LSH hash family. Specifically, let a distance R and approximation ratio C And given that we have an RCR P1, P2, LSH hash family for some distance d, then there exists an RCR approximate near neighbor structure which works with high probability and has subsquared construction time and space, but most importantly, has sublinear query time. Hence, to give an approximate near neighbor structure for polygon retrieval based on the shape, we aim to create RCR P1, P2, LSH families for our distance functions. This concludes our detour to approximate near neighbors and locality sensitive hashing. Here are our results in a high level. We built an LSH-based RCR approximate near neighbor data structure for bounded integrable functions. Specifically, we designed approximate near neighbor structures for the LP, the vertical invariant LP distance, and the vertical and horizontal invariant LP distance, both for P1 and P2. The L1 structure is given using an LSH hash family, where all 5 other structures are given via reductions. All our structures require subsquared extra space and preprocessing time and have sublinear query time, each with a different coefficient. For polygons, we also give RCR approximate near neighbor data structures for polygons with a bounded number of vertices. We first proved some interesting bounds on the turning function of polygons with at most m vertices. Next, we apply the previous LSH-based approximate near neighbor structures from functions to the turning functions of the polygons to get RCR approximate near neighbor structures for the polygon turning function L1 based and L2 distances. That means that we get a polygon approximate near neighbor data structure, which is efficient and returns perceptually similar polygons, which are invariant transformations. We now go through our results, building them up from approximate near neighbor structures for the aligned distance to structures for vertical and horizontal shift invariant distances, and finally bounding and applying them to turning functions of polygons to give similar shape retrieval structures. We start with the structures for the aligned distances. Recall the LP distance between 2 functions f and g. Our goal is to design an LSH family for the L1 and the L2 distances. Recall the L1 distance, which is the area between 2 functions. Specifically, the L1 distance between the black and the red function is precisely the green area. We give our L1 distance LSH family for bounded integrable functions as follows. We first define a hash function h given a point P in the rectangle which contains the graphs of f and g, which is the rectangle 0, 1 by A to B. We map each function to 1 if it's above the point, and map a function to -1 if it's below the point. Here f is below q, so it's mapped to -1, and g is above q, so it's mapped to 1. Our hash family is all such hash functions defined by a random point in the rectangle which contains the graphs of the functions. That is a point which is uniform in the rectangle 0, 1 by AB. To see that this hash family is an LSH hash family, we observe that 2 functions f and g collide specifically over hash functions h of p, where p is not between the graphs of f and g. It is easy to see that, for example, since hash is defined by points which are above both functions, give -1 to both functions. Hashes which are below both functions give 1 to both functions, and hashes defined by points which lie between the graphs of f and g map one of the functions to 1 and the other to -1. Therefore, the probability of hash collision over a random point in the rectangle is equal to the red area over the whole rectangle area, which is effectively 1 minus the blue area over the rectangle area, where the blue area is precisely the L1 distance between the functions. Hence, for any 2 functions f and g, we can see that for the hash above, the probability of collision is 1 minus the L1 distance over B minus A. This means that any pair of functions which are near each other have a high collision probability, and any pair of functions which are far from each other have a low collision probability, which means that this is an LSH hash family. The immediate corollary using Indyk, Motwani, and Harpellet's result gives that for any R and any C, there exists an RCR approximate near neighbor structure for the L1 distance for n functions with ranges bounded in AB. This structure requires sub-squared extra space and pre-processing time and has sublinear query time with the following row, which is smaller than 1. We now give a structure for the aligned L2 distance. In the paper, we give two solutions for L2 distances. The first is an LSH directly for L2 distances based on the LSH that we've presented before, and the second is a reduction to Euclidean distances. In this reduction, we sample our functions f and g at evenly spaced points I over n, and normalize appropriately by dividing by square root of n. This effectively transforms each function to a vector, and we observe that the L2 distance between the functions is well approximated by the Euclidean distance between the vectors, and the approximation improves the larger the n we take. This gives a straightforward structure that given R and C, we first compute a sufficiently large sample size nRC, then we replace each data and query function f with a quantized vector form, and then we store and query all functions using an approximate near neighbor structure for the nRC dimensional Euclidean distance. We use, for example, the spherical LSH of Andoni and Rosenstein. Since our structure uses spherical LSH internally, we present its guarantees. The spherical LSH data structure is an RCR approximate near neighbor structure for the d-dimensional Euclidean distance, which has the order of d times n to row query time and requires order of n to the 1 plus row space and order of d times n to the 1 plus row processing time, where row is as follows. From our reduction to Euclidean distances, we get the following corollary. For any R and C, there is an RCR approximate near neighbor structure for the L2 distance for functions. Its performance is similar to that of spherical LSH, but a specific selection of variables gives a slightly diminished row value of 1 over 2c minus 1. Now to the shift invariant distances. We call the vertical shift invariant LP distance, which looks at the minimal distance over all vertical shifts of one function, which is the black one here, to the other, which is the red one here. Our goal is to design approximate near neighbor structures for the vertical shift invariant L1 and L2 distances. Note that we have several difficulties. First, even computing this distance requires solving a minimization problem. And second, the optimal value depends on both f and g. So there's not one pre-processing which would optimize this. Our solution is to approximately reduce the vertical shift invariant distances to regular L1 and L2 distances using what we call the mean reduced transformation. To define the mean reduced transformation, let f be a function and let f bar be its mean. We define the mean reduce of f to be the function minus its mean, and denoted by f hat. This is this function. Notice that since the mean reduce of f has mean 0, the green and red areas are equal. We observe that the mean reduced transformation tends to vertically align functions. With the function f above and the function g below, these functions are not aligned. However, if we consider the mean reduce of both, we can see that they are almost optimally vertically aligned. This is not by chance, and we have proved that for any two functions f and g, the mean reduced transformation optimally vertically aligns the functions f and g. That is, the vertical shift invariant L2 distance between f and g is the regular L2 distance between the mean reduces of the functions. On the other hand, for L1 based distances, we show that the mean reduced transformation gives us a 2 approximation. Specifically, the L1 distance between two mean reduced functions is at least and at most 2 times the vertical shift invariant distance between the functions. In the paper, we improve this bound and show an approximation ratio which is strictly below 2. This approximation is stronger when the vertical shift invariant distance between the functions is known to be large. The proof of this approximation appears in the paper, and we believe that it is of independent interest. The approximation schemes above give us a data structure for the vertical shift invariant L1 and L2 distances by replacing each function with their mean reduce, storing everything in a regular approximate near neighbor structure for the regular L1 or L2 distance. And given a query, simply query the approximate near neighbor structure with the mean reduce of the query. This scheme fetches data functions for which the mean reduce is near the mean reduce of the query, which by the approximation above means that the vertical shift invariant distance of the functions is low. We extend the previous structure, which already handles vertical shifts, to handle also horizontal shifts, that is, to be an approximate near neighbor structure for the actual turning function distance we care about, which is the vertical and horizontal shift invariant distance. By the definition of the vertical and horizontal shift invariant distance, if we use the previous structure, but replaced each data function with a set of all possible horizontal shifts of it, inserted all of them to the structure, and given a query function, queried the structure as is, then this would work. However, since there are infinite many possible horizontal shifts, we instead consider a quantized and constant set of such shifts for each data function. In order for the reduction to succeed, the remaining question is, how fine should the quantization be? Since the functions we consider are in fact turning functions of polygons, a small horizontal shift does not drastically change the L1 distance, and therefore the quantization of horizontal shifts does not need to be too fine for the structure to contain an approximate optimal horizontal shift. Now that we have all our structures for functions, we apply them to the turning functions of polygons. Our goal is to give efficient structures to find similar polygons to an input polygon. As I've just mentioned, the solution is to apply the structures from previous sections to the turning functions of polygons. First, we fix an upper bound on the number of vertices in the data inquiry polygons, and recall that to apply the structures for function distance, we need the data functions and the query functions to be bounded. Hence, we need a bound on the range of turning functions of polygons with at most m vertices. We indeed give such a tight bound. We show that for any polygon with m vertices, the turning function is bounded between approximately negative m over 2 times pi and m over 2 times pi. The construction of the polygon which achieves this bound involves successive folding into a spiral shape and is described in full in the paper. To conclude, we present novel LSH-based approximate near neighbor structures for searching nearest neighbors of both functions with respect to the L1 and L2 distance and extensions of them, and for polygons with respect to the shape similarity using the turning function L1 based and the L2 based distances. We also give tight bounds regarding turning functions. Recall that the mean reduced approximation for the vertical shift invariant L1 distance has a ratio slightly below 2. An interesting open question is if this bound can be strengthened when we focus only on turning functions and not general functions. Another interesting open question is if there exists an approximation scheme similar to the mean reduced transformation to reduce horizontal and vertical shift invariant distances to vertical shift invariant distances. Thank you.